Yes.
Okay, thank you. Also, I'm just going to remind you all, as usual, when I'm sharing my screen, I cannot see the chat section in the side. So if you'll have any questions, please unmute, feel free to unmute yourselves and speak to me, ask me the question, whatever it is, because I won't be able to see the chat section, all right? And once again, don't forget to send your student number and your full name on the chat section. Okay, let's start. So example number 5, and I believe I didn't make it for yesterday's lecture. I only attend the double on a Tuesday. So some of your classmates told me that he completed the rest of the examples yesterday. For those that were in his lecture, in the lecturer's lecture yesterday, in Machine's lecture, um, you would be just recapping everything that was done. Okay. Let's look at example number 5. It says a 3000 kilowatt, 6.6 kilowatts, volts, sorry, a frequency of 60 hertz, speed of 200 RPM synchronous motor operates at a full load at a leading power factor. If the synchronous reactance is 11 ohms, calculate the following: the apparent power of the motor per phase, the AC line current, the phasor E naught, and draw the phasor diagram. Also determine the mechanical angle alpha. All right, let's go into our memo. And let's do this. Okay. Or just ignore the first part. It's question number 4 from the previous session. Okay. Right. So write down all the information that you have. Okay. We know that our power is given to us 300 kilowatts, but what power is this? This is 3-phase. So go and put down 3-phase. It makes your life so much easier. And the volts that is given to you is also in 3-phase. 60 hertz, 200 RPM, operates at full load, power factor is 0.8, leading, and your synchronous reactance is 11 ohms. All right, and we are neglecting the losses. All right, so we have to calculate the apparent power. What is apparent power? Is S is equal to P in divided by cos of theta. P in, and that phi angle thingy is my notation of per phase. All right, so for 3-phase, that's how I write it, 3 and then phi, and for per phase I just write phi. All right, so please don't confuse yourselves and think that that is an angle, because it's not. I'm just indicating for myself that in order to get the apparent power per phase, I'm going to take my power input per phase and divide it by cos of theta, which is nothing but your power factor. Are we given the input power? Yes, we are, but we are given in 3-phase. We want single phase per phase. So we just divide that by 3. Once again, I'm repeating myself. Don't go and divide by square root of 3. Don't confuse yourself with power and volts. When you want power per phase, you divide by 3. When you want volts per phase, you divide by square root of 3. So in this case, it is 3. And then divide by power cos of theta. Cos of theta is just your power factor, which is 0.8. And that's your answer. 1250 kVA. Sorry about the scratch. Ignore that. kVA. All right. Let's go on to the next one. So far, it's pretty simple. The AC line current. B says calculate the AC line current. So I denote it with I and a subscript L, and that's what I want. Okay. So I know that the input power per phase is actually equal to E times I times cos of theta. Do we have P in? Yes, we have. Do we have E? Yes, it's given to us. Do we have cos of theta? Yep. Do we have the current? No. That's what we want. That's what we're looking for. So it's just one straightforward formula. You make I the subject of the formula, and this is what your equation will look like. So what is your P in? P in is 3000 times 10 to the 3 divided by 3 because it's per phase. And is E given to us? Yes. It's 6,600 volts, but this is in 3 phase. We want it in per phase. So you can see that I went and divide by square root of 3. Multiply by your cos of theta. Once again, cos of theta is nothing but your power factor. Multiply that by 0.8, and this is the answer that you are going to get. Okay. Where did I get this angle from? If you put this into your calculator, you're only going to get a magnitude of 328.04. Okay, so where did I get this from? Pretty simple. What is power factor? Power factor is just cos of theta. And in reality, what is cos of theta? What is theta? Theta is the angle between I and E. So it's our current angle, all right? So we can go and just calculate that simple grade 11 maths, grade 10 actually. Cos of arc cos of 0.8, and you get an angle of 36.87, and that is the angle for your current. All right, don't forget your units. Also, guys, if you are not in the habit of multiplying it by 10 to the power 3, when it's in kilowatts and stuff like that, you don't have to, okay? I liked doing that, so I did it, but you don't have to. Okay. I can see there's quite a few students that joined now. For those that joined now, welcome. And today we'll be completing the examples that was done by your lecturer yesterday. So we're basically doing the examples on synchronous motors, and we completed question 1, including right up to and including question 4 last week. I mean this week on Wednesday, and today we're going on to question 5. This is question 5. These were the given information we needed. The first question said apparent power. That's how we calculated apparent power. It was pretty simple, and now we just calculated the current. Okay, and this session might end in the next 30 minutes or so, or 20 minutes. You are required to join part 2, but before you do that, you have to send me your student number with full name on the chat group here, all right? For attendance purposes, don't worry, nothing else. Okay, let's go on to C. C says that calculate the phasor E naught. Right, let's go and calculate that. We know our golden rule, all right? I feel like this kind of equation, in fact, this equation itself answers so many different types of questions. It's like so many different types of questions. And you'll see the pattern once you start repeating and doing the tasks like more than 2 to 3 times. Okay. So E is equal to EX plus E naught. This is simple maths from our phasor diagram, and I think it's also explained in your notes. Okay. This is just the formula. We want E naught. So E naught will just be E minus EX. Okay. It's not a big deal. But in this case, what is our EX? Our EX is equal to I times J times XS. Okay? I times J times XS. And also, our E is given to us. You can just put this straight here. I don't know why I went and calculated it separately. I think it was for my simplification, my own simplification. So this just comes from taking our voltage that is given to us and dividing it by square root of 3. Then your I, we just calculated our I, and that's the value for our I. Just substitute that in with your angle, please. That is the reason why we calculated our angle here. Okay, and we just didn't give the magnitude. Thereafter, it's your J, and then your synchronous reactance is given to be 11. Okay, once you put that into your calculator, don't forget that this is an angle, so make sure your calculator is in complex form. All right, and that's how you go about calculating, and this is the value that you will get. Okay. The next one says determine the mechanical angle alpha. Oh, I don't know if you guys are noticing this, but this type of question is coming out very frequently in the examples that we've been doing for the past 2 weeks. Okay, this mechanical angle. What does that tell you? Go and learn the formula, basically. Okay, sorry, that's the last question. For now, we have to draw the phasor diagram as well. Okay, so we have all the information that we need. Now we need to calculate draw our phasor diagram. So E, we know that it's a straight up, right? But E is 3810.5. It is not 6,600 volts, okay? You write your per phase value, don't forget that. Then you go straight to your I. The next step is to go straight to your I. Your I, you calculated it to be 328.04. That's your magnitude. What about the angle? That's your angle, but is it upwards or downwards? Is it leading or lagging? The question says it's leading, so it will be on top. And the angle between the two will be 36.81, which we've calculated using the power factor. Similarly, E naught, we got the value of E naught to be this. And what angle did we get? We got a negative angle. What does that tell you? It's going to go downwards. All right. And of course, EX will just be this line here connecting the two, E and E naught. And then I wrote the value for EX. One more thing to take note of. Oh, by the way, the parallel of this, another line, will be here. All right. I think your lecturer included that, like a dotted line, like an extended line here. I didn't. One more thing to note is that the length of the lines actually depends on the magnitude. So we know that E naught is 6,637.19 and E is actually smaller than that, is smaller than E naught. So the lecturer doesn't expect you to go and, make E like longer than E naught. Okay, this was supposed to be a little bit more extended, but I put it at that length because it is showing that it's greater than this value here. And please make sure that you substitute all your values onto your diagram so your lecturer can follow as to what you're doing, what your interpretation was. If there was any misunderstanding, if you misinterpreted the question, he will be able to see it and give you fair marks according to your working and stuff like that. So make sure that your lengths it doesn't have to be accurate, but it shows that E is actually smaller than E naught, and I is actually smaller than both of those values. All right, so keep an eye on that. Yeah, so we just did the phasor diagram, and the last sub question for this says that determine the mechanical angle. So let's go back. And we know how to calculate the mechanical angle. It's not a train smash, it's just 2 times this angle, which we've just calculated. There you go. Delta divided by P. And then this is the answer that you get. Okay. I think that was a pretty simple example. It wasn't so difficult. I'm just going to be here. I know some of you like to take notes. You can take notes. I'll give you 2 minutes and then we can go on to the next question. Okay. Okay, I know most of y'all took screenshots. So let me just go down. Okay. And there you go. All right. Let's go to the next question. Here's the next question. Let's just take a minute and read it. Okay. A 1500 kilowatt, 600 RPM, 60 Hertz. Synchronous motor possesses a synchronous reactance of 16 ohms and stator resistance of 0.2 ohms per phase. Okay, the excitation voltage is 2400 volts and the moment of inertia of the motor and its load is that value there. We wish to stop the motor by short-circuiting the armature while keeping the DC motor current fixed. You are required to calculate, A says, the power dissipated in the armature at 600 RPM. Let's go and see our memo. All right, so this is the information that is given to you. All right, your J is given to you as well. And it says that breaking of the motor by short-circuiting the armature. The first question is asking you to get the power in the armature at 600 RPM. So at 600 RPM, your Z, which is your impedance, is equal to XS squared plus RS squared. Okay, your synchronous reactance and your stator reactance. So when you sub the values, which is given to you, into the formula, you get the value of 16 ohms. All right. And thereafter, you go and calculate your current. Okay. What is the value of your current? Current is nothing but E naught divided by Z. And E naught is given to us. All right. There's it here. And sorry, just 1 minute. I feel like there's something off here. Okay. Okay, wait. Yes, E naught is given to us to be 2400. I didn't write it here. Yes, it's 2400 divided by Z. And Z is 16. So your answer comes to 150 amps. If you guys want to take down the notes for this substitution, it's 2400 divided by 16, giving you 150 amps. Okay, we are required to calculate the power. All right. So you're going to say P is equal to 3 times I squared times R. Okay, so it will be 3 times 150 all squared multiplied by 0.2, and this is the value that you get. Okay, this was at 600 RPM. Now, if you look at question B, B says it's the same question, but now we're talking about the speed is at 150 RPM. So you're going to ask yourself, or you're going to ask me like, okay, Parveen, what is going on? You said that we're talking about 600 RPM over here, but we don't even use this value, you know, in our calculation. So what is the difference in the question? Okay, here's the difference. This relationship is what defines both the questions, okay, and separates them, differentiates them. So this equations explains what we're talking about and what is needed from us. Ix is fixed, and we know that E naught is actually proportional to N, which is your speed, okay? But your synchronous reactance is also proportional to your frequency. But then in return, I'm not sure how many of you did power elec already, but you know that frequency is actually related to speed as well. So if you change the frequency, if you change the speed, the frequency will change. And if you change the frequency, the speed will change. So if you are changing your speed, what is it going to affect? It is going to affect your frequency. So if you're changing your speed, it's going to affect your frequency, which in turn is going to affect your synchronous reactance. Are we using synchronous reactance in this question, in this solution? Yes, we are. So do you see what is changing? So the relationship starts from here. I'm going to repeat myself once again. The synchronous reactance is dependent on the frequency. Frequency is dependent on the speed. If the speed changes, frequency changes, which in turn makes the synchronous reactance change. And if the synchronous reactance change, do we care? Yes, we care. Why? Because we are using synchronous reactance in our solution. Okay, so what was the first step that we did here is that we calculated the impedance. How did we calculate the impedance? We said it's the synchronous reactance squared plus RS squared. All right. So now our synchronous reactance changes. So you're going to ask me, okay, so by how will it change? What is the equation? Well, there's no equation. There's no actual equation actually. What happens is that you can see that your speed was 600 RPM here, and now in this question it's 150. What does that mean? It means that the speed in question A was 4 times greater, all right, then it is in B. You agree? 4 times 150 is 600, all right. Similarly, the reactance in A will be 4 times greater than that in B. So what is the reactance here? 16. So what is 1/4 of 16? 4. And that's how we get the reactance of 4. And that was the trick in this whole question, basically. All right. And same thing, repeat the same thing, same order, and you get your answer and your power as well. All right. Let's look at C. Guys, this meeting will be ending in the next like 7 minutes. So if it ends, just join part B. All right, I'll start part B. Once again, don't forget to send me your name, your full name, and your serial number on the chat over here. Okay, let's look at C. C says the kinetic energy at 600 RPM. So kinetic energy is equal to 5.48 times 10 to the negative 3 times J times N squared. All right. Do we have our J? Yes, it's given to us. It's in our question. So this is a constant. Multiply that by your J, squared by your speed that is being asked, and that's the value that you get. It's pretty simple. So the only trick in this question, according to me, what I think was this relationship that you had to identify. Okay. So let's look at the next question. The next one says the kinetic energy at 150 RPM. No problem. Let's go. Same thing. It's just that your n will change now. So it'll be 5.84 times 10 to the negative 3 times j times n squared. And that's the value that you will get. Okay. Let's look at E. The time required for the speed to fall from 600 RPM to 150 RPM. So now we're talking about the time that it is required for the speed to decrease from 600 RPM to 150 RPM. Okay. This is the relationship actually. So, okay, let's calculate our W first. Okay, so this is the equation. It's going to be in your notes. I made it pretty simple, but your lecturer has quite a bit of information and explanation about this, but I went and used the equation straightforward. So P is equal to W divided by T, and we want the T, all right, we want the time. So we need to calculate the difference between the two energy levels, all right, the kinetic energies. So that's what we did. It was a pretty straightforward thing, all right. I just took this minus that, and I got a value for my W. Okay, and then P is given to us. When you substitute it into the formula, that's the value that you get. Okay, that was simple. Okay, and that brings us to the end of question 6. Okay, and I'm going to end this meeting in the next minute or so and start the other one. All right, and then we can continue on question 7 and perhaps 8 as well if we have time. Yeah. So send me your details here. Okay, so question number 7 says that a synchronous capacitor is rated at 160 MVAR. Okay, and the voltage is 16 kilowatts, speed is 1200, frequency is 60 hertz. It has a synchronous reactance of 0.8 per unit and is connected to a 16 kilovolts line. Calculate the excitation voltage denoted by E naught so that the machine absorbs 160 MVAR. Okay, and the next one says deliver. Also draw the phasor diagram in each case. Now this looks like a type of a question that will blank out a lot of students, including myself. But it's actually not so difficult if you know your notes. Let's see. The only thing that you actually need to know in this question, the trick in this question is that the fact that A says that it absorbs, the word absorbs, that's the only like tricky part. All right. It says that it absorbs, so and so, value. So when it says it absorbs, it means that theta is actually negative 90 degrees. That's what it means. That's all, nothing else. Okay, so let's go about calculating this. It's a little bit long, but it's not like terrible. Okay. 1 minute, I'm just going to verify something very quickly. Yes, all right. So we are calculating E naught. All right, remember I told you all that this equation is like a solution to almost all the questions, the type of questions you get. So E is equal to E naught plus EX, and E naught is actually equal to E minus EX. All right. Break this down even further, that you will get E minus EX is, if you break that down further, it's I times J times XS. What is XS? Your synchronous reactance. But in the very first session, we spoke about how the synchronous reactance needs to be in ohms and not per unit. If they give it to us in per unit, it's a bit of a problem. We'll have to go and, convert the whole thing and make it into ohms. That's exactly what we have to do here. It's given to us in per unit, so you have to multiply it by the impedance, base impedance. All right. So remember, this is our goal. Don't forget what is our goal. Our goal is to get this value here. In order to get that value, we are using this equation. We have almost everything that we need in this equation. We have to calculate everything that is in this equation. Okay. I believe the only thing that is given to us is the E. And of course, you have to put it in per phase. That's why it's square root of 3. Everything else you have to calculate. So you have to go and calculate I, and you have to calculate XS. So let's calculate XS first. How do you calculate the synchronous reactance? By multiplying it by the impedance. How do you calculate the impedance? Well, impedance is just EB squared divided by SB. And so you have to calculate this even further. Do we have EB? Yes, it's just 16K, but that's in 3-phase. We'll get it into per phase. That's not a problem. But we don't have SB. So that is what we're going to calculate. And that is where we're going to use their given details, all right, of 160 mega. Okay. So that's where it comes into the picture. So I'm going to repeat myself. We are calculating E naught. In order to calculate E naught, we need XS, I and XS, but we'll calculate I later on. but we need XS first. So in order to calculate the synchronous reactance, you multiply what is given to you in per unit, multiply that by impedance. In order to calculate impedance, you need your voltage, which is given to us, and you need your power. All right, S. But this S is not, is actually, it is given to us, but it's in three phase. So we're just making it into per phase. And then you can simply go and substitute this value into this equation. Sorry, let me just use my spotlight. Yes, so you can take this and substitute it into your formula, and that's the value that you will get for your synchronous, your impedance. You use the impedance value and calculate your synchronous reactance. So in order to calculate synchronous reactance, you need your impedance. In order to calculate your impedance, you need your power. It is given to us, but it's in three phase. Divide by 3, and you get it in per phase. Okay, you can do all of this in one step, but I broke it down. And then substitute everything back into the formula, and this is the value that you get for your impedance. Once you have your impedance, then substitute it here, and you get your synchronous reactance. Okay, that's a lot of talking I did. If you guys got confused or don't understand, please unmute yourselves and tell me, because once again, I'm not able to see the chats. Now what we need to get our E naught, we need I. I is our current. So how do we get our I? There's a formula that you use in order to get your I when you have your power. That formula is nothing but S per phase divided by E per phase. Do we have S per phase? Yes. There's it here. We calculated it. Do we have E per phase? Yeah, you just take the value 16K and divide it by square root of 3. And it is at what angle? Negative 90. That was the trick here. It's negative 90. And when you substitute this into your calculator, this is the value that you get with a negative angle. Take this value, the yellow ones, go to your equation, the lifesaver equation, substitute everything here, put it into your calculator, and this is the value that you are going to get. Note that when you do this, you're going to get a value for your angle to be 0, which kind of makes sense because we're calculating E naught. Okay, we know that E is usually 0, but in this case, our E naught is also 0. And what will happen to our I? Our I will go straight down negative 90 degrees. Why? Because it is absorbing. Okay, so it's going to go straight down to 90. See? Don't do this. I just put a rough sketch. Go and draw it nicely with your ruler, and make sure that the lines, the length of the lines are dependent on the magnitude. Okay, don't forget that. My laptop battery is like dying, so I'm just going to put it in charge and be back in like 1 minute. Okay, so that's how you solve 7A. All right. And I will leave 7B where it says delivers, so and so power up. I'll give you all a chance to calculate that. And the only tricky part in that is the delivering part. So when it's absorbing, the theta angle is 90 degrees. So what happens when it's delivering? When it's delivering, then it's basically positive 90 degrees. All right, so now your I vector is going to be facing upward straight at 90 degrees. That's basically the only difference. You can follow the same method and go and calculate 7B. You can have a look at your lecturer's solution as well for this question, and I'm sure you'll be able to do it. Moving on to 8, quite long. Give you all a minute to read. Okay, let's analyze the question. First line, it says that it's delta connected. This is very important to note that it is delta connected. Okay. Another thing is that it says 2.05 ohms per phase, and friction and windage are 1.5 K. And of course, the power factor is 0.8 and it is leading. Let's look at the first question. It says determine the supply line current, IL, the armature current per phase, the excitation voltage per phase, and draw the synchronous motor phasor diagram. Okay, that's a lot of stuff. Okay. Let's look at question example 8. So delta connected means that your VL is actually equal to your V phase. And that's why we don't need to change the E that is given to us into per phase. Okay. So everywhere else we were changing it to per phase by dividing it by square root of 3. So here we don't have to do that. And I think that was the trickiest part in this question. So let's see. Let's calculate. Yes. Trimira, was that you? Okay. The line current is nothing but this value here, and we get this by using this equation, your input power. Okay, guys, I did all of this just to make my life easy. Like, I just wrote stuff down. I went and wrote my efficiency formula and all of those things just to, so I get to know where I'm standing, if I write down all these values. So we know that P in is equal to 3 times E times I cos of theta. Okay, and we want I. Okay, we want our line current. So in order to calculate your line current, you need your I, which is this value here. And can we calculate our I? Yes, we can, because we have all of the other values. Okay, so let's see. Do we have cos theta? Yes, it's given to us. Do we have E? Yes, it's given to us. And do we have P in, the input power? Not exactly, but all the information is given to us in order to calculate P in. Okay, when I say that, I mean like, the output power and the total losses. So when you calculate P in, this is the value that you get, and you just simply substitute it into this formula. So the main thing in this, in these type of questions is that you know what you are looking for. I know I'm looking for my line current, all right? And in order to do that, I'm going to need my power input, and I'm going to need my I, and I'm going to need cos of theta. So I worked backwards, and that's what I calculated. So that's why it's important that you write down this information, all of this. Okay. And that's the value that you get, okay? Now we need to calculate E naught. So once again, the very famous equation, E is equal to EX plus E naught. So you got your E naught, and you're just substituting values into your E naught, okay? So you have your I, you have your XS, it's given to us, we just calculated I, and then you have your E. once you put that into your calculator, this is what you get. Sorry, it's kind of like clustered. I didn't leave a lot of space when I was doing this question, but I think it's a little bit readable. Now let's go ahead and draw the diagram, phasor diagram, just like how the question asked us to do. We know that E is straight and we have the value for E, okay? We also have the value for cos theta, which is 36.78, just arc of what's given to you, and you'll be able to solve that. And we calculated I, right? We just calculated I. So draw your I. Is it leading or lagging? Your question said that it is leading, so obviously it's going to face upwards. Then your E naught, when you calculated your E naught, you got a negative angle, which indicated that E naught actually lies below, and that's the value of your angle. It's 12.41 if this is not visible. And we know that EX is nothing but joining E naught and E, and the parallel component of that will come here. And that's what I was missing in the previous question when I told you all that I left that extended part out. Okay, remember again to draw the phasor diagram according to the values. It doesn't have to be accurate, but you must be able to differentiate when you look at a line which is longer and which is shorter. Okay, let's look at question B, 8B. Assume that the shaft load is now increased to 22.38 kilowatt and determine the excitation voltage per phase, E naught again, in response to this change in load. Okay, so increase the load angle will increase what? It will increase the magnitude of the voltage. Let's see. So increasing the load will increase the angle, but the voltage remains the same. Yes, so increasing the load will increase the angle, but the voltage will remain the same. So let's see, we know that our Ix is constant, okay, and the magnitude of E naught is also constant because of this, okay? So our power output is 22.38 kilowatt, and your power input, we calculated that to be 24.88. Okay, here you are accumulating your losses and putting your output power, and that's what you get. Remember, this is in 3-phase. Then you can use the power equation, and your power equation in this case will be we use this equation on Wednesday, if you guys remember, E times E naught sine of delta divided by XS. Okay, so what we want in this case is we want delta, because what is delta? In theory, delta is basically our E naught angle. Remember, the angle for our E naught, that's delta. So make sine theta the subject of the formula on the next page, and this is what the equation will look like. We have all of these information, just need to substitute it into the formula, and this is what you get. So remember our value for E naught was in the previous question was 255.09 at an angle of negative 12.41. In this question, when you are increasing the load, sorry, I might have said this incorrectly earlier, but when you increase the load, the angle increases, but the magnitude, that means the voltage, remains the same for E naught. That's what it means. So we did all of these calculations just to get the angle. All right. And we got 255.1 from the previous question, and it just changed the angle. Okay. And when you write it in vector form, that's what it would look like. Okay. Ignore this. This was my test venue. C says that determine the armature angle per phase, armature current, per phase I, the supply line current IL in response to this change in load, and draw the synchronous motor's phasor diagram for this new operation condition. Let's see. So we have to calculate our I, okay? But in order to do that, let's go and look at our main equation, okay? So E is equal to EX plus E naught. And when you simplify that further, this is what you get. We want I, so make I the subject of the formula, simple maths, and this is what you will be left with. You have all the information that you need. Just put it into your calculator, and this is the answer that you will get. In order to get the line current is nothing but square root of 3 multiplied by the current that you just got. Okay, same thing in the previous question as well. So you got your line current sorted. I don't think I drew the efficiency diagram. Oh no, I did, but it's on the other page and I forgot to include it into the PDF. Sorry guys, but your lecturer does have this. He has all the solutions and everything there, so you can go and have a look at the phasor diagram. Okay, but I just wanted to show you like the main steps over here is just the manipulating of this equation in order to get your line current. Okay. The next one says determine the new motor power factor and the efficiency of the motor following this change in the load. Okay. So we know that power factor, I broke it down into two questions. We know that power factor is nothing but cos of the angle. All right. And cos of angle what? The current angle. What current angle? We're talking about what we just calculated due to the change. And when you do that, this is the power factor that you get. Why is it leading and not lagging? Because we had a positive value and not a negative one. Efficiency is a simple formula. Efficiency is equal to power output divided by power input multiplied by 100, and you get the efficiency to be 89.95. And that brings us to the end of today's session. I think your lecturer will be continuing with the tutorial. Yes, the tutorial questions next week. So if you'll attend the session on Tuesday, I think he will be doing the tutorial, the entire tutorial. Maybe I'm not too sure. So you just have a week more before your test, and it's not that difficult if you'll do it like at least try and do it 2 to 3 times. I know you'll have a lot of stuff, but try to do it 2 to 3 times, and you guys should be fine. Okay, it's the mastering of the questions, like how you go about analyzing the question.